Okay, welcome to the Nomenclature of Basic Inorganic Compounds presentation. This is part one of several parts. I'm not exactly sure at the moment, but this may be a 4 or a 5-part presentation, simply because of the type of material that we are going to cover, and also just the number of things in the book as far as skill sets, the number of items. So this is Chapter 7, but I'm not really going to go along with Chapter 7 for the first two sections. I'm going to present a different way on how to write the names of compounds, how to name them, and how to write their formulas. The book will present their way. I have a way that I'll present to you, which was adapted from a different textbook. And in the end, you'll be able to name and write the formulas for the same types of compounds. However, it's just a different strategy on how you learn the rule sets. So here we go. We're not going to use a student learning map for this particular unit. You can look over this. Certainly it's an important question and important key learning. However, I'm going to ignore this for the test. Also, again, if we are not going to consider the student learning map, we don't have to worry about this, but the question is relevant for naming ionic compounds. Okay, there are a few things to keep in mind. So the next few slides are about keeping things in mind. I would draw your attention back to when we talked about the periodic table. If you take group 1 and group 2 and combine it with groups 13 through 18, that becomes what we call the main group of elements. And in the main group of elements, there are various patterns that arise in that set of 8 columns. And most predictably, most importantly for us, is the predictability of the valence electrons and their charges when they lose or gain valence electrons. We had talked about this before before school let out, and so that should be, I think, as a reminder, that should be something that you can refresh yourself on pretty quickly. Okay, so other details to remember going forward. I would remind you that the s orbital and the p orbital of any atom of any element make up the entire valence electron shell. That's why there can only be up to 8 valence electrons, because you cannot fit any more electrons in the s and p combined. 2 in the s, 6 in the p. Remember that the octet rule states 8 valence electrons is the most stable configuration. And remember that there are a few elements that will stabilize with less than an octet. They will actually stabilize, such as like helium, actually. So here we go. Other things to keep in mind, that polyatomic ions cannot exist by themselves. So ammonium is a polyatomic ion we talked about before the break. And ammonium has the formula of NH4 with a positive 1 charge when it's in that configuration. That would be 1 nitrogen, 4 hydrogens. And if you count the valence electrons, it is missing 1 that it actually should have. But it's intentional because it's an ion at that point. But what you're looking at is only part of the story. You're not seeing why it is ammonium. Ammonium, I can't just hand you a jar of ammonium. Now, this is different from ammonia, the household cleaner. Different product, different chemical. Ammonium is an ion, and there's no such thing as handing you a jar of ammonium. It's always got to be hooked with something. There's got to be a reason for ammonium to exist. So if it were to bond with chlorine, we could have ammonium chloride, and the chloride allows for the ammonium to exist. This is true with all polyatomic ions. Ammonium happens to be the only positive ion, polyatomic ion. All of the rest that I am aware of are negatively charged, meaning they actually gain electrons from other atoms. But they can only exist when they are in compound form. So just realize that. And lastly here, all compounds are most stable when they are completely electrically neutral. Even if they're made of ions with charges, the charges should overall cancel out to make a neutral compound. And we'll see that going forward. Okay, ions. If we were in school, I'd have you memorizing the ion table completely. And to be honest with you, you going to college, if you have not memorized this table and you go and you take a college chemistry course, I really think that you will be at a deficit in that the students before you who had to memorize that table because the quizzes, you couldn't look at the table to take a quiz, that I believe they were better for it. And a lot of reports coming back from students who have gone to college and taken chemistry is that even though it was very arduous for them to memorize all those ions, it was very, very beneficial when it came time to revisit all of this in a college chemistry class. So I would strongly encourage you to memorize them anyway, but there's no way for me to check. So, good luck, and just one of the maybe chemical sacrifices of COVID, right? Okay, just to remind you that here is the current ion list. It doesn't really change much. I've added a few over the years, but this is pretty much what has been the ion list I've used for years and years and years. The ones that we were kind of getting ready for was the variable cations, where we have a number of metals that can do more than one thing. They can lose 1 or 2 or 3 electrons or more, and they can do it under different circumstances. And so we had this variable cation list. And then we never got to it yet, but this is a list of polyatomic ions, and you will need to consult this list going forward. Remember, these never exist by themselves. They will always be ionically bonded with something over either in the monoatomic cation list at the top, or the variable cation list at the bottom, or in rare cases, any of these can bond with ammonium, which is the only positive ion in this particular list. Now, there are some others that I have listed for reference that I never have anybody memorize because they're somewhat rare and unique, but they're there just if you need to look them up. And I've included a couple of extra things at the bottom for future chapters, so this is kind of a little more versatile list. Okay, a little bit of vocabulary. The term oxidation number, sometimes called oxidation state, is simply referring to the charge of the ion once it has either lost or gained valence electrons. So, for instance, aluminum's oxidation number is a 3 positive charge, and that means it has lost 3 electrons, lost 3 negatives, therefore its overall 3 positive charge because the protons outnumber the remaining electrons. In phosphate, even though the P and the 4 oxygens, so PO4, those are all internally covalently bonded together, this whole unit can act as an ion, as if it's one atom, not 5. And as like one atom, it can actually gain up to 3, and it has to gain actually 3 electrons in order for it to do its bonding and become stable. And so its oxidation number is a 3 negative charge. Okay, ionic compounds. Ionic compounds are electrically neutral when the number of electrons lost by the cation is equal to the number of electrons gained by the anion. Now, there's a way to figure out the formulas, and that is through what we call crisscrossing the oxidation numbers. It is a shortcut for creating correct formulas to create neutral compounds, which means that you've accounted for all the electrons lost have been gained, all the electrons gained were lost. So it's an accounting. For all ionic compounds, all subscript should be reduced to lowest terms. Polyatomic ions, so this PAI is simply an abbreviation for polyatomic ion. Polyatomic ion formulas cannot be changed. Even if you're reducing everything else, a PO4 must remain PO4. An NO3 for nitrate must remain NO3 if it's indeed a nitrate. We'll talk more about that going forward. Okay, so I have adapted a naming system for the rules for naming and the rules for formula writing from a different textbook written by this guy named Stephen Zumdahl. And he's written a number of different textbooks for all levels, from 9th grade kind of chemistry, intro chemistry, all the way up through PhD level. And he developed for high school a very good system for naming and formula writing. And for him, it's more about labeling. He groups rules together and he just gives it a label, and it makes it very easy to remember from my point of view. So if you're looking in the book, it will not line up with this, but it will, in the end, we'll all be able to name and write the formulas for all the same compounds, regardless of which method you prefer. Okay, so just an overall overview of the Zumdahl labeling system is right here. This is kind of a two-page, two-slide outline, I guess. So what he calls a type 1 compound. These type 1 compounds are ionic. And they are composed of our monoatomic cations. Remember from your ion list, that is the top 4 boxes. So anything out of those top 4 boxes would be your monoatomic cations combined with any anion. Now that would be the middle 3 boxes of negative ions like nitride, oxide, and those, or any of the polyatomic ions on the back of that sheet. They are also anions. They're negative. Now, we will include ammonium because ammonium functions just like a monoatomic cation. So we'll throw that in there and we'll call all of this type 1. We'll have a simple set of rules on how to write names and how to write formulas for these what we call now type 1 compounds. Then he goes on and he creates a type 2 compound, and they are also ionic. But these will be different because there is a variable cation. So that's your table B out of that ion list. That's the table B. So any of those variable cations would be the first thing written down, and then again combined with any anion, which is the 3 boxes on the front that are all negative and all of the polyatomics on the back, which are all negative. We will also investigate compounds called hydrates, and hydrates are found in both type 1 compounds and type 2 compounds, and it's basically just water groups. A hydrate is just a water group, one or more water groups that have been trapped with the chemical, with the compound as it formed, as it crystallized, and we have to account for that. If it's present, we have to account for it, right? The rest of his system is the type 3 compounds, which are all of his covalent compounds. And all of his covalent compounds are pretty simple, and they are nonmetals combining with nonmetals. So that'll be pretty easy to figure out, like carbon dioxide, CO2, carbon monoxide, CO. You know, those are examples of type 3 compounds, and they're very familiar to us. His type 4, I actually broke up into kind of 2 categories to keep them straight. The type 4 acids, or the type 4 compounds, are acids. Now, while they are covalent compounds, they are sharing their electrons, we will be able to treat them as if they were ionic. So that's kind of very fortunate. The first kind of type 4 acid we'll talk about are binary acids. These are acids that are made of hydrogen combined with a nonmetal. So over here's the general formula. Hydrogen combined with any nonmetal, and that's a short list on the periodic table. So that'd be like hydrogen and chlorine to make hydrochloric acid, a very common acid. The type 4 acids we'll also talk about, which are covalent, are what are called ternary acids. And these are simply composed of hydrogen combined with, in this case, a polyatomic ion. So anything from the back of that sheet that could combine with hydrogen will create what we call a ternary acid, simply meaning that there is more than 2 elements in that particular compound. Okay, so we'll get to all of those, and I will take each one of these in part. So each one of these will have its own little narrated video, and once we get through this first longer video to kind of get the whole show started, the rest of the videos themselves, the presentations, should be much shorter. Okay, what about crisscrossing? So let's talk about like how to write formulas and how to determine formulas. Okay, here is the process. So ions, crisscrossing, and neutral compounds. Consider an ionic compound that is formed from calcium and oxygen. Okay, so how many calciums do you need? How many oxygens do you need? And what will be the formula? What is the ratio? And how many valence electrons are exchanged between the two because they are ionic? Also, I would like you to consider in the middle, aluminum and oxygen. Same situation. How many aluminums do you need? How many oxygens do you need? How many valence electrons are exchanged? And then lastly, let's consider aluminum again, but now let's have it combined with a polyatomic ion, a PAI, a polyatomic ion, nitrate, which is NO3, and nitrate has the ability to absorb or gain 1 electron, so it functions as an NO3 -1 ion group. Okay, so we'll consider these in order. So first, let's do calcium and oxygen. And I will use Lewis dot diagrams to kind of illustrate the idea before we get to what is called crisscrossing, which is an incredible shortcut. Okay, so here we have calcium and oxygen, and I'll go from the top down. So calcium has a Lewis dot diagram of 2 dots because it comes out of group 2 and they all have 2 valence electrons. Oxygen coming out of group 16 has 6 valence electrons, and when they're neutral and when they're just stationary, there they are. Now, consider that a calcium and an oxygen atom collide, high energy collision, just a random motion collision. What happens? Well, oxygen has a very large, very high level of electronegativity. It is a very strong attractor of electrons. Calcium has a low level of electronegativity. It's a weak attractor of electrons. So therefore, when this collision occurs, oxygen not only will keep its own electrons, but it's going to steal permanently calcium's electrons. So valence electrons will be transferred, and I'm showing that with these blue arrows here. Notice oxygen has a gap here and a gap there for an octet, and that's where those electrons would eventually bond if we're showing through Lewis dot diagrams. Well, what happens after that? Well, we have a calcium that's lost 2 valence electrons, so it now has an official 2 positive charge. That's its oxidation number, its charge. Oxygen has gained these 2 electrons. Now, normally I would just show them as regular old black dots, but I'm trying to illustrate the difference, so I've showed them a different color here. That's not, you don't have to do that, but it's just something to visualize. And this oxygen now has 2 extra electrons over neutral, and so it's a 2 negative charge. So the ions form and they attract each other because they're oppositely charged. This creates the ionic bond. These charges, notice a 2 positive and a 2 negative cancel, so the charges cancel and creates a neutral compound. Well, what's the ratio? It looks like for every 1 calcium, all I need is 1 oxygen because it's a perfect match. 2 to lose, 2 to gain. And you only need 1 atom of each to make that happen. So the ratio is a 1-to-1 ratio. So I could write this Ca with a subscript 1, O with a subscript 1, or we don't need to write the ones. If you write the symbol Ca, you got one of them, right? And if you write oxygen O, you have one of them. So the formula for calcium oxide is CaO, and that's why it's a 1-to-1 ratio, as you can see by the Lewis dot diagrams above. Let's now consider the next example, which was aluminum and oxygen. And this will take part over, I think, 2 slides because there are various transfers I want to show you. Okay, here we go. So consider then, same kind of method here. Let's consider aluminum and oxygen here at the top, both being neutral. So here's aluminum with its 3 valence electrons coming out of group 13. Here's oxygen again coming out of group 16 with 6. So the first collision occurs, this oxygen being highly electronegative and aluminum being lower electronegativity can steal. So oxygen can steal 2 valence electrons. After this, the collision yields this. So here we have oxygen gaining 2 electrons, it's 2 negative charge. This oxygen is now stable, it has an octet. But what about this aluminum? Notice this aluminum has lost 2 electrons, it has a 2 positive charge, but it has an extra valence electron, which is causing it to be unstable. Aluminum will not remain in this condition long because of the instability of having that 1 additional electron. So what happens? Well, consider wherever you have 1 aluminum, you have a quadrillion. Wherever you have 1 oxygen, you have a quadrillion. So what's to say that this aluminum that needs to lose an electron still can't collide with just another oxygen in the test tube? So here's what that looks like. So here's the first oxygen. It's stable. It's not doing anything. Here is aluminum, and it combines with this oxygen and loses its remaining valence electron. So this collision, the second collision, yields aluminum with a 3 positive charge. That aluminum is now stable. Remember, its octet is actually now created from inner shell electrons, as opposed to this oxygen down here, which is now in the same boat that the aluminum was a moment ago. It is almost, but not quite stable. It has a -1 charge. It has 7 valence electrons, but it really is needing 8. Well, remember, where there is 1 aluminum, there's a quadrillion. Where there's 1 oxygen, there's a quadrillion. And oxygens can only collide with aluminums. If they collide with other oxygens, nothing really happens. So what happens next? Go to this slide. What about a third collision? So let's now bring in a second aluminum. That second aluminum, it's fresh with 3 valence electrons, collides with this oxygen, transferring 1 valence electron, and this yields this situation. This aluminum hasn't changed, this oxygen hasn't changed. This one is now stable with an octet, 2 negative charge, but this aluminum is in the same boat the others were at the previously. Now I have 2 valence electrons causing instability. Well, of course you see the pattern. Let's bring in another oxygen. And here we go. So here is my third oxygen. This third oxygen collides with the aluminum, stealing these 2 electrons. This collision comes over to here. Notice this aluminum has now lost all 3 valence electrons. It is now stable with the 3 positive charge. This oxygen, which was the only one that was unstable, over neutral and unstable, has 2 valence electrons extra. It now has its octet and a 2 negative charge. Notice everything is officially now stable. Everything has an octet. Look at the charges. 3 positive and 3 positive is an overall 6 positive. 2 negative, 2 negative, 2 negative is an overall 6 negative charge. 6 positive, 6 negative cancels. 6 electrons transferred, lost and gained. Everything matches up. Okay, so here is then the final arrangement, and here's the summary. For the proper valence electron exchange, it will take 2 aluminums for every 3 oxygens to create this neutral, stable compound. It's a 2 to 3 ratio. Therefore, the formula becomes Al2O3, the formula for aluminum oxide. This is how we can determine that. All right, so let's move on to the next last example, which was aluminum and nitrate. Oh, and by the way, just to pause here, this is the entire process all in one page if you want to just glance at that, just showing you stepwise. Okay, here's the last example. Okay, so I have aluminum at the very top. I have a nitrate, which is an NO3 grouping, also at the top. So that whole thing is called nitrate. It has 1 open spot for an electron. Well, in a collision, the aluminum transfers 1 electron over to the nitrate, yielding aluminum with a 1 positive charge, not stable because it still has 2 valence electrons, and a nitrate, which is now perfectly stable. Everything has an octet in that nitrate grouping, and if you were to count protons to electrons for this entire group, you'd find that there's actually 1 extra electron that doesn't cancel things out. So it's a -1 charge for the entire unit. Rather than doing this stepwise, I'm just going to show you the whole thing. So here's my 1 aluminum. Here I would need 3 nitrate groupings because they can only gain 1 each. So I bring in the 3 nitrates. The collisions occur, the electrons are transferred, yielding 1 aluminum with a 3 positive charge and 3 independent nitrates, each with a -1 charge. They all attract each other, positive to negative. That creates the ionic bond in the compound, and the compound is electrically stable and neutral because 3 positive and 3 1 negatives cancel out. So what is the formula? 1 aluminum to 3 nitrates, and here's where I got to keep nitrate in a formula. I have to put it in parentheses so this 3 can multiply this whole thing, saying I've got 3 nitrates. If you didn't have the parentheses, it would look like you had 33 oxygens, and obviously by the diagram you can tell there are not 33 oxygens. Okay, now, while Lewis dot diagrams are a great way to see this electron transfer and to count the atoms and determine the formula's ratio, therefore the subscript, is there an easier way? Oh, yes, there is. We will use what is called a crisscross system. It doesn't have a fancier term than that, just the crisscross system, in order to use the charges, crisscross them to create these subscripts. Let's see how that works. Okay, the crisscross method, to determine the subscript for ionic compounds. Okay, so the crisscross method kind of runs like this. So here I have aluminum with my 3 valence electrons. Here I have my oxygen with my 6. I know aluminum can lose 3, oxygen can gain 2. Well, I don't want to have to do all of that stepwise again, so let's move down to here and check out aluminum. So aluminum having a 3 positive charge and oxygen having a 2 negative charge once they have officially lost and gained. If I simply write them this way, ignoring the Lewis dot diagrams, if I write them like this, ignoring the Lewis dot diagrams, 3 positive charge, 2 negative charge, if the numbers do not match, if it's 3 and a 2, they don't match, I crisscross them and create them as subscript. I move them down into the subscript position and I lose the positive or the negative sign. If I do that, I have the formula Al2O3, and that gives me the correct notation for aluminum and oxygen. For every 2 aluminums, I need 3 oxygens. And you can verify by going back a few slides and checking that that was indeed the case with the Lewis dot diagrams. Notice with calcium and sulfur, Calcium has a 2 positive charge. Sulfur actually has a 2 negative charge. 2 valence electrons to lose, has 6, needs to gain 2. So that's how that works. Notice the numbers are the same, 2 and 2. When they're the same, I do not need to actually crisscross these. I can simply eliminate them and realize that 2 lost and 2 gained is a 1-to-1 relationship. So I can just squeeze them together and write the formula as CAS. So I simply just cancel the numbers, cancel the charges, and write it as a formula. Okay, now sometimes we do have to reduce to lowest terms. This happens more with the variable cations than it does the monoatomic cations, but it could happen. So when we reduce, we will never, ever change a polyatomic ion formula using this method, but there is some reducing that can happen. So consider a compound created between hafnium with a 4 positive charge and selenium with a 2 negative charge. Well, the 4 and the 2 don't cancel, so I crisscross. When I crisscross, what do I get? Well, when I crisscross, I get HF2SE4, which is great. I've crisscrossed. For every 2 hafniums, there are 4 seleniums. But notice the 2 and the 4 can reduce to lower terms. I divide them both by 2, and I get this 1-to-2 relationship. So I only need 1 hafnium and 2 seleniums in order to actually make the electron transfer happen, and it creates a neutral compound. Cool, great, love it. I get it. But, Spence, do I have to actually reduce when possible? Yes, you do, because this is not, this HF2SE4, this is not a formula that is recognized for hafnium selenide. This is the formula down here in the reduced form. Okay, moving on. Okay, let's officially get to the type 1 compounds. And I strongly recommend you, I know this is going long, but it's all intro material. It's all very important. But if it gets long, just pause it. Come back to it. Know where you stopped and just pick it back up again. But I'm going to keep going because it's the presentation. So type 1. What is a type 1? Well, according to Stephen Zumdahl and me, type 1 compounds are ionic compounds that are formed from the chemical combination of monoatomic cations, remember those top 4 boxes, including ammonium, and anions, anything negative on that ion sheet, front or back. Monoatomic cations, that's the definition. Anions, that is the definition. Certainly pause and take a look at it. Okay, what are the rules? Well, here are the rules if you want to go from the formula to the name. From the formula to the name. Okay, so if I have a formula like NaCl, right? Sodium chloride, NaCl. Well, how did we get that name from NaCl? Well, first of all compounds begin with a monoatomic cation that is named with its first, it is named first with its full name. This includes the polyatomic ion ammonium, and we'll use the word ammonium. The anion is named last. Now, if the compound ends with a non-metal anion, so that would be pretty much from the front of your ion list, nitrogen, oxygen, etc. If it ends with a nonmetal anion, we will use the IDE ending that you were memorizing for all of those quiz sets that we kind of started and never completed. So nitrogen is really nitride when it's in a compound, and this is what you memorized, and we will stick with that. So all nonmetal anions will end IDE, just like the sheet has, oxide, nitride, sulfide, chloride, fluoride, etc. If, however, the compound ends with a polyatomic anion, we will use the full name of the polyatomic anion and we won't change it. We'll just use it. Like nitrate will always be named nitrate if it's functioning as a polyatomic ion. What about some examples, Spence? Well, I've got some examples right here for you. So check this out. We have MgCl2. So if we want to name it, the first substance written down is the cation. So here's our monoatomic cation, and it's named with its full name first. So magnesium. Then you're going to name the chloride last. So magnesium chloride, IDE, because it's last and it's the anion, so you're going to use that IDE suffix. So magnesium chloride. What about this? This is going to be, again, named magnesium, cation named first with its full name, and the anion is now a polyatomic ion. So I'm going to simply just use its name. So magnesium nitrate. And if you start to memorize those polyatomic ions, you will just be able to kind of wrap that off really quickly without having to look up on that sheet for the 100th time. Oh, NO3, what is it? What is it? What is it? If you memorize it, it just saves so much time. I strongly encourage you to memorize that ion list, even though I'm not there to make you do it, right? Or at least encourage you to do it. I don't think I can make you do anything. Okay, what down here? Sc is scandium, full name, cation, full name, scandium. N is nitride, so scandium nitride. Here I have the polyatomic ion. The only one that can be written first is ammonium. And then we have SO4. You look that up. It's a polyatomic ion, and that would be ammonium. And this thing is called sulfate, ATE, sulfate. So ammonium sulfate. Then I have down here Ba, which is barium, and then PO4 we had on a previous slide, a polyatomic ion called phosphate. So this is barium phosphate. All of this is, of course, coming from the ion list. So here is your monoatomic cations all across the top, and here is the nonmetal anions there, right? Of course, the polyatomic ions, like we just had, like right in here, we had nitrate, we had sulfate a moment ago, and phosphate as well. So here are the names, correctly written, correctly spelled, showing you the answers. I'm going to move on. You can certainly pause if you want to write that down. And I encourage you to be taking notes throughout this entire presentation. All right, well, what if you have a name like sodium chloride written down, with the names, and you want to go to the formula? How do you do that? Well, here are the rules to figure that out. So first of all, you will write the elements and or polyatomic ions down in order from the compound name and assign correct oxidation numbers. If the oxidation numbers are the same, you simply cancel them and you rewrite the formula. It's a 1-to-1 relationship, like the calcium and the sulfur from earlier, Ca2 positive, S2 negative. The 2 positive and 2 negative cancels, so just CaS. And that was on that previous slide. So that's what we would do there. Well, what if they don't cancel? Well, if they don't cancel, like aluminum and oxygen did not cancel, 3 positive, 2 negative, this slide here explains, hey, if they don't cancel, you gotta crisscross them. So crisscross the oxidation numbers, make them subscript, drop the positive, drop the negative, all right? And if a polyatomic ion is involved, good idea to group it in parentheses, especially and necessarily if there is subscript that will go outside the polyatomic ion. You got to keep it in parentheses. We had nitrate a little while ago with aluminum nitrate, had to stay in parentheses for the formula. Without the parentheses, it would have looked like 33 oxygens. So the new subscript would be placed outside the parentheses. Remember to reduce any new subscripts to lowest terms if possible. It happens sometimes, especially more with the variable cations, but if it does, do it. And you have to. Now, we will never ever, though, look in and modify a polyatomic ion formula. So you can't reduce this. It doesn't matter. It's got to stay PO4. Finally, rewrite the new formula with the new subscript and without oxidation numbers. Of course, examples follow. So here we have sodium sulfide, tantalum nitrate, silver acetate, and you can read the rest. So what are they going to look like? Well, I believe if I flip the slide, we just get all of them. So I'm going to flip the slide and we'll just talk about it. Okay, so sodium sulfide. Sodium has a 1 positive charge, so I wrote down Na positive. Sulfide is S2 negative. The charges did not cancel because it's a 1 and a 2, and so I have to crisscross. When I crisscross, the 1 comes down to sulfur, the 2 comes down to sodium, giving me Na2S, and I can't reduce that. Moving down, what about silver acetate? Well, silver is Ag with a 1 positive charge, and acetate, a long-written polyatomic ion, is all of this with a -1 charge. Well, +1, -1. They cancel, so I just rewrote the formula. I didn't need any new subscript at all. What about ammonium nitride? Ammonium is NH4 with a positive 1 charge. Nitride is nitrogen. It's 3 negative. Well, the 1 and the 3 don't cancel, so I crisscross. And when I crisscross, the 3 comes down to the ammonium. I need to leave the ammonium in parentheses because there is a 3 there, indicating you have 3 of these groupings. If you don't have the parentheses, obviously it looks very different. And only 1 nitrogen, so NH4 3N is that formula. And if you pause it like that when you say it to somebody, that gives them the idea of what it should look like written down. What about indium oxalate? Well, 3 positive, 2 negative. Oxalate is the C2O4 grouping you will find on the back of your ion sheet. And the 3 and the 2 don't cancel, so I crisscross, and when I do that, this is the formula that I end up with. Okay, well, the others kind of work out. So tantalum nitrate, barium sulfate, you can see how those work out. Notice really quickly here with thorium sulfite. Now, there is a sulfate, ATE, and a sulfite, ITE. This occurs a few times on your polyatomic ion sheet. Please make sure when you're looking these things up, if you haven't memorized them, that you're looking them up correctly because they are easily mistaken. Well, thorium has a 4 positive charge, and this sulfite grouping has a 2 negative charge. 4 and 2 don't cancel, so I must crisscross. So there's my little crisscross arrows. When I do that, I would have TH2, right? SO4 or SO3 in parentheses with a 4 outside. So TH2SO3 4. Well, I would reduce that because the 2 and the 4 would reduce, and this would be the final formula. So it happens on occasion. Pay attention for it, right? And this is the only formula that would be acceptable for thorium sulfite. Sodium hydroxide, you can see it's a 1-to-1 ratio. Okay, just a reminder on the polyatomic ions, here's the entire sheet that I was able to capture with like a screen capture. And so just looking down through this, remember that ammonium is the only -1 charge. And I know it's a pain, I strongly encourage you to memorize this list. Memorize the front. I would ignore these in this box. You know, those are great for looking up, but they don't come up very often. But these are very, very common. They come up quite a bit. And there's not a lot there, actually. Notice chromate and dichromate. They're very similar in formula, and they have the same charge. Hydrogen carbonate, hydrogen sulfate, hydrogen sulfite. Carbonate, sulfate, and sulfite are on this chart in other places. This is just with a hydrogen there. Well, the hydrogen bonded to it reduces the charge down to -1. They also have another name called bicarbonate. Many people have heard that name, bicarbonate, before. Nitrate and nitrate, notice NO3, NO2, just the variation of 1 oxygen but the same charge. Phosphate and phosphite, PO4, PO3, here again, just 1 oxygen different, same charge. Sulfate and sulfite, same situation with a 2 negative charge. By the way, phosphate, the only ones that have a 3 negative charge, so those are easy to memorize. You get down here to the perchlorate, chlorate, chlorite, ITE, and hypochlorite. Excuse me, ClO4, ClO3, ClO2, ClO. All -1 charge, and notice the pattern, 4, 3, 2, 1, per, 8, 8, ite, hypoite. That's the system. It's basically a variation on Latin prefixes, suffixes. Notice with iodine and bromine, the same pattern exists, the same formula exists, except for the substitution of iodine or bromine. So when you get down to this chart, it looks daunting. It looks like it's a lot. It's not actually that much, and it is so critical to your success. If you have some of these or all of these memorized, then you don't have to continually flip this chart over and look for it. It's kind of like having some of the elements on the periodic table memorized. If you have the top half memorized and you run into an element that you don't, then you know it's on the bottom half. It cuts your time significantly looking for things if you haven't had them memorized.